Good morning, everyone. I hope you're doing well. I hope you had a great weekend. Welcome to the lesson on graphing polynomial functions. I know you're pumped about getting a video lesson today. First off, if anyone has any homework questions on day 2, which was solving polynomials using technology, probably Desmos, please feel free to ask me on Wednesday. I'll answer all questions you have. But until then, let's get to today's lesson. Now, first off, the first set of questions I have are, what is the degree of the following polynomials? And what is the leading coefficient? So we had a question like this on a previous quiz. Some of you got it, a lot of you didn't. So let's review. How do you find the degree of a polynomial? That's actually a two-pronged answer. So finding the degree of a polynomial, finding the degree of a polynomial, if the polynomial is not factored, like it is not in number 1 and number 2, the degree is just the one term, the monomial term with the highest exponent. So in number 1, I am going to add up the 3 and the 2, and the degree of this polynomial is 5, because that's the term with the highest exponent. The leading coefficient is the coefficient that goes along with that leading term. So the leading coefficient is a -4. Okay, for number 2, the degree is the term with the highest exponent. So that's 10. So this is a 10th degree polynomial. The leading coefficient is the 33 that goes along with it. Now look at number 3. It's a bit different. This polynomial is already factored for us. So if the polynomial is factored, you are going to add up the exponents of each factor to determine the overall degree. So actually what I'm going to do is I'm going to use a different colored pen here. I'll go with red because that's what I had right here. This is an exponent of 1. And if I add up the 2, the 1, and the 3, 2 plus 1 plus 3 is 6. So the degree of this polynomial is 6. It's a 6th degree polynomial. And what's the lead coefficient? Well, how would you find the lead coefficient? Well, if you FOILed all this, this would be 1x times 1x times 1x, or it'd be x to the 6th power to lead the way. So the leading coefficient, if you did FOIL it all out, would be a 1. Okay. So with that said, we are now going to talk about what these might look like on a graph. Okay, and that's the basic purpose of today's lesson. Now, today's lesson is going to be twofold. The first part of this lesson is to determine what the overall shape of the graph is going to look like. The second part of this lesson is going to be figuring out where the graph hits the x-axis and what happens at those points. Does it cross straight through the x-axis, or does it bounce off the x-axis? I am getting ahead of myself with this, so let's start with phase 1 or part 1. Okay, what does the overall graph look like when you have a big polynomial? Okay, so there's a chart here, and instead of doing this chart and doing algebra, why don't we discover right now? So I'm going to share my screen with you. I'm going to share Desmos, and I'm going to put in y equals x shift 6 squared. And I get a parabola. That's what this is called. It's a U-shaped parabola. Pretty cool right there. Perhaps you've heard of a parabola before, but that's what x squared looks like. Now, what if I delete the 2 and I put 4 instead, x to the 4th? Ooh, kind of looks like a parabola. How about x to the 6th? Parabolic shape, yeah, x to the 8th. I think you're getting the point here, 10. Okay, so what's going on here? It's parabolic, but the point is, I want you to notice something. Notice how it's starting by going up to the left and it's finishing by going up to the right. Now, what if I stuck a negative in front of the x? It's going to go down. Let me see, if I go back to negative x squared, it's a downward parabola. Now, I am corny. You know this by now. If you don't know by now, you will know. But watch this. As dumb as this sounds, this is the way I remember. If it's positive x squared, the parabola is smiling at you. It's a smiling parabola. Aww. If the parabola is negative, it's a frowning parabola. It's a sad Charlie Brown song. It's going to be a frowning parabola. Okay, so if I go back to my, and I share with you my sheet again, the notes. If it's an even powered function, like y equals x squared, or to the 4th, or to the 6th, or to the 8th, okay? Or dot, dot, dot. The graph is going to start by going up and end by going up. Those are called, I call them the ending arrows, how it begins, how it ends. What if it is y equals negative x squared, or to the 4th, or to the 6th, or to the 8th, dot, dot, dot? Well, that's going to be a frowning parabola. So it's going to start by going down, and it's going to end by going down. That's the end behavior. That's what this is called right here. So this is when the exponent is even powered. That's what the even stands for right there. Okay, so what if I go back to Desmos right now and I share with you, what if I get rid of that negative, but now instead of x squared, what if I say x to the 3rd power? Ooh, I call this in mathematical terms the wiggle, because it goes up, it wiggles its way through the x-axis and then continues up right there. But I want you to notice one thing. It starts by going down and to the left and continues by going up and to the right. Another term I give for this besides the wiggle is going up the stairs, because you're going up, then it goes flat. It's like you're stepping on the origin. You're stepping flat there, and then it goes up. I call it up the stairs. But if I do x to the 5th, also the same, going up the stairs. X to the 7th, up the stairs. X to the 9th, up the stairs. Let's go back to x cubed. What if I put a negative in front of it? Ooh, now I'm going down the stairs. I'm starting on the top left, and I'm ending on the bottom right. I'm flattening out on the at the origin here. So I'm going down the stairs. Same thing if I do negative x to the 5th, or the 7th, or the 9th, or the 11th, or the 13th, or so on and so forth. Okay, so if I go back to my behavior chart right here, if I have a positive leading coefficient and it's positive x 3rd, or 5th, or 7th, or 9th, or so on and so forth, how does this graph look? Wiggle. It's a parabola that goes up to the right and then it goes down and to the left. But bottom line is you start at the bottom left and you finish at the top right. If I have y equals negative x to the 3rd, 5th, 7th, 9th, dot, 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 I'm going down the stairs. I'm going up to the left and I'm going down to the right. Okay, so I'm going to call this up the stairs. And I'll call this going down the stairs. And if I went back to my parabolas, this is a smiling parabola. Yay, it's smiling. And this is a frowning parabola. Wah, wah, frowning parabola. Okay, so now that we have this down, let's put this together and talk about overall degree and behavior. There are only 2 end behaviors if you think about it. There's parabolic shape or parabola shaped. I'll say, is it parabola shaped or is it stairs shaped? If the exponent is even, it's parabola shaped. If the exponent is odd, or if the degree is odd, I shouldn't say exponent. If the degree is even, it's parabolically shaped or parabola shaped. If the degree is odd, it's stairs shaped. Then go one step further. If the lead coefficient is positive and it's even, it's smiling. If it's odd, you're going up the stairs. If the lead, if the lead coefficient is negative, if the degree is even, you're frowning. If the degree is odd, you're going down the stairs. Let's put this all together here. Let me zoom out and let's do some of these questions right now. I'm going to have to scroll back up and down. All right, so what's the overall degree of number 1? The overall degree of number 1 is x to the 4th. And the lead coefficient is positive 1x to the 4th. So this is even. It's positive, so it's parabola shaped. And that means I'm going to start by going up and end by going up. My leading term in number 2 is x to the 3rd. So this is a 3rd degree polynomial. That's odd. So I'm either going up the stairs or down the stairs. but the leading coefficient is negative. So I'm going down the stairs. So I'm going to start at the top of the stairs and go down. These are just quick sketches, by the way. This is not exactly what the graph's going to look like. It just gives me an indication. I'm going to start at the top left, and I'm going to finish at the bottom right of an XY axis. Okay. At any point, I'm going to stop right here. At any point, pause and replay any part of this video if I'm going too quickly, or if you didn't understand a certain part and you want to hear it again. Pause, rewind, and replay. Number 3, this is a 5th degree polynomial. All right, so it's degree 5, which is odd, and the lead coefficient is positive. So that's going up the stairs. So I'm going to go up the stairs, which means I'm going to start at the bottom of the steps on the bottom part of the XY axis and finish on the top right part of the XY axis. Last but not least, this is the degree. The degree of this polynomial is 10. The lead coefficient is negative, which means I have a frowning parabola shape. It's even, so it's parabolically shaped, and it's negative at the lead coefficient. So I'm going to start down and end down. That's how you could tell. Some of these polynomials look pretty difficult, but if you just break down the end behavior, at least you know where you're going to start and where you're going to end the graph. All right, ladies and gentlemen, let's move along here. What are some common forms of named graphs? Linear functions, y equals mx plus b. You've seen all that before. Anything with x squared, any parabolas are actually called quadratic functions. Here's a common quadratic function right here. All right. Anything with x cubed is called a cubic function. Anything with x to the 4th is called a quartic function, and so on and so forth. I'm not going to give you any examples because we just did. And what do I mean I just did? I gave you the examples of end behaviors. That's really all I want to make sure that you understand for class right now. These main end behaviors. Okay, so I'm going to skip right past these graphs. And we're going to get to the lesson. Here we go. All right, before I fill in this chart, I'm going to go back to Desmos one more time, and I want to do an example with you just to make sure we have the rest of the lesson down. Okay, so here we go. Give me 1 second. I got to find my new share, and I'm going to go back to Desmos. Here it is. Let me get rid of all this, and I am going to put a parenthesis, and I'm going to say x plus 3, close parenthesis, and then I'm going to hit shift and do squared, and then I'm going to do parenthesis, and then I'm going to do x minus 2, close the parenthesis, and then I'm going to start another parenthesis and do x minus 5, close the parenthesis, and I'm going to say shift to the 3rd. And it looks like just some nasty looking thing right here. Wow. Okay, so hold the phone. If I zoom out on this, you could see that this, oh my gosh, you know what? I might just have to fix this up right here. Okay, because it's very difficult to see here. By the way, I just made this up. I just made this up. So I might have to make this up again. I might have to just get rid of just one thing for a second. Let's see. All right, good. You know what? This is all I'm going to say for right now. Sorry, I know I'm bouncing around, but I just wanted to do a picture that I could show you. Okay, if I zoom out just a little bit more, there's what the graph looks like. But I want you to notice something. Where is this thing crossing the x-axis? Do you notice how it's crossing the x-axis at -1, right at -3, and it's crossing the x-axis at +2? Yes, I hope you noticed that. Now look at the function. What if we were on day 1 and day 2 of this unit? We solved polynomial functions. What if you set this factor equal to 0, x plus 3 equal to 0? What would you get? X equals -3. -3 is where it hits the x-axis. Coincidence? No. If you go back a couple days, one of the names for a solution was called the x-intercept. There's the connection. If you could see me, I'm just holding my head and going right now. How about this? This crosses the x-axis at 2, so the x-intercept is 2. If you solve x minus 2, set it equal to 0, you get x equals 2. Wow. So The other thing I want to point out about this, notice how the factor of x plus 3 has a squared attached. It's an even power. Notice what it does at x equals -3. I come up to the x-axis, but instead of going through the x-axis, I bounce off the x-axis like a little parabola would. Remember, x squared is a parabola. So when you have a factor that has an even powered exponent, when you get to the x-axis, you don't go through it, you bounce off that exponent. Notice x minus 2 has no exponent at all, or does it? If it did, it would be a 1. Notice how the graph didn't change when I put that 1 there. But notice how at x equals 2, I go up to 2 where 2 is, and then I go straight through that power. Just for kicks and giggles, what if I change that 1 to a 3? It does a little wiggle through it, but notice how it still goes through the x-axis at x equals 2. So we're going to go back to our notes right now. The main point of what I want to illustrate with you through Desmos is when the exponent of the factor is even, you bounce off the x-axis. When the exponent of the factor is odd, you go straight through the x-axis. Let me go back to our notes here. So we are going to, I'll do this in red, we are going to bounce. Ooh, didn't change immediately. We're going to bounce off the x-axis at the 0 if the 0 occurs an even number of times. In other words, if the exponent of the factor is even, we bounce off the x-axis. We are going to, I'm going to say, go straight through the x-axis if the 0 occurs an odd number of times. In other words, if your factor has an odd exponent attached to it, you're going to go straight through it. 1, 3, 5, 7, 9. This might sound confusing. Some of you, Mr. Claude, I wish you were here in school right now because I don't understand this. Don't worry. Let's do some examples, 2 or 3 examples, and you might say, I think I actually get this now. So let's do example 1. First and foremost, the end behavior is found by finding the degree of the polynomial. So first, it's a factored polynomial. So let me put the exponents of the factors and let's add them up. 2 plus 1 is 4. So 4th degree polynomial. And the lead coefficients of all these are just a 1, a 1, and a 1. They're positive. So it's positive x to the 4th. So what does x to the 4th look like? Let's zoom back up. It's even and it's positive. So it's a positive leading coefficient and it's even. It's parabola. More importantly, it's parabola up. It's smiling at us. So I know it's going to start up and end up. So watch this. Keep that in mind. I'm going to just draw a little quick sketch here. It's going to start up and end up. The next thing I'm going to do is I'm going to solve each of these factors. So it's x minus 1, it's x minus 2, and it's x minus 3. If you did what we did back, in day 1 of this, you'll get x equals 1, you'll get x equals 2, and you'll get x equals 3. So 1, 2, and 3. So watch what I'm going to do. On my graph here, I'm going to put points on the x-axis at 1, and 2, and 3. Wherever the roots or the zeros are, that's where I put points on the x-axis. Next, I am going to apply the end behavior. I am going to draw an arrow that goes up to the left of the first root or the first 0, or the first point on the x-axis, and draw an arrow that goes up to the right of the rightmost point right here. It starts going up and it ends going up. I'm almost done here. This is where the exponents of the factors come into play. Notice I circled these numbers, but I kind of forgot them for a second. Let's remember them now. This is a 2 right here. This is a 1 right here and a 1 right here. This is personally what I do. Not every teacher does this. I do this. Okay. I'm going to attach those exponents to each of these roots. Okay. Now, why would I do that? Because this lets me know that the root of 1 is a double root. It happens twice, but that also lets me know that I'm going to bounce at that root. Why? Because any root or any factor with an even exponent, you bounce at. For these two right here, they're both odd, so I'm going to go straight through those roots. So watch what I'm going to do. I'm going to get in my car, and here's the horrible sound effects. I'm going to come down to the first root, but it's a double root. The one has an exponent of 2, so I'm going to go to it, and I'm going to bounce off. Bounce with me. And I make a little mini parabola. Then I'm going to come down to the second root, but it's has an exponent of 1, so I'm going to go straight through it. Then I'm going to come up to the third root, but it's also odd, so I'm going to go straight through it. And look, I end up right where I'm supposed to end up. And I'm done. Problem is finished. I bounced at the first root because it had an exponent of 2, and I went straight through the next two roots because they had exponents of 1, which were odd. Mr. Colodi, how high should I go in terms of going up there? How low should I go with this point right here? Don't concern yourself with that. I'm going to erase those arrows right there. Don't concern yourself with that. The thing that I want you to concern yourself with more than anything is the end behavior of the graph, where the roots are, and the behavior at each root. Do you bounce at the root, or do you go straight through the root? Some of you may still be confused. Let's do some more. Okay, here we go. Let's get to it. First, I'm going to put an exponent of 1 here. I always put an exponent where I don't see one. This is a factored polynomial, so I'm going to add up the exponents. 1 plus 3. This is a degree 4 polynomial. And these are positive x's, so it's going to be a smiling parabola. How do I know that? Because this is a positive 1x and that's a positive 1x. Okay, so to get my zeros, I take x minus 2 and solve it. And I take x minus 1 and solve it. Do I need to do this side work, Mr. Colodi? No. I mean, after a little while, you understand that you get 2, you get 1 here. So my advice, and this is huge advice, put the roots in numerical order. Okay, remember, this is x minus 2 to the first power, x minus 1 to the third power. So I'm going to put a 1 and then a 2. Put them in numerical order, and then attach the exponents to each one. But both of these are odd exponents. So both of these I'm going straight through. All right, so let's just cut to the chase here. I'm going to put a dot here at x equals 1. I'm going to put a dot here at x equals 2. And because it's a smiling parabola, I'm going to start with an arrow going up, and I'm going to end with an arrow going up to the right of the rightmost. You put an arrow to the left of the leftmost and an arrow to the right of the rightmost. And then at each one here, I'm going straight through. So straight through the first, straight through the next. Believe it or not, I'm actually done with that problem. You're kidding me, Colodi. That's it? Yeah, I'm not kidding you. It's a 4th degree polynomial. It's positive, so it's a smiling parabola shape. And I'm going through each of the roots because both have odd exponents. I'm done. Wow, that's really not that bad. Okay, let's do the next one. Uh-oh. Number 3 is not factored. How do we find the degree when the polynomial is not factored? You just take the highest exponential term. So this is a 3rd degree polynomial, and it's positive 1x to the 3rd. So that means I'm either going up the stairs or down the stairs. And since it's positive, my overall shape is up the stairs. I'll start at the bottom of the steps on the bottom left part of the xy axis and finish at the top. All right, so to find the zeros, let me write this all over again here. X cubed minus 2x squared. This might be the last example I do with you in these notes. Minus x plus 2. I'm actually going to go through the rules of factoring here. I'm going to group. Oops. I'm going to group. I'll take out an x squared, and I'll be left with x minus 2. I'll take out a negative 1, and I'll be left with x minus 2. Then I will write my factors, x squared minus 1 and x minus 2. And I'm done. Oh, wait, I'm not done. X squared minus 1 is a difference of 2 squares. So then this breaks down into x plus 1, and x minus 1. Oops, did one too many parentheses there. And then I also have the x minus 2 coming along for the ride. I think it's fully factored now. Keep in mind, each of the exponents of each of these factors, I don't see them, so they're ones. 1, 1, and 1. So if I draw my stick here, I'm going to get negative 1, positive 1, and positive 2. But when I could just skip, just put the exponents by them right there, and there they are. There are my 3 roots with exponents attached. They're all odd, so I'm going to go straight through each. So that's what I'm going to do here. I'm going to put a x value right there at negative 1, at positive 1, and positive 2. Okay, so here we go. I know that I'm going to start at the bottom of the stairs and go up to the top. So to the left of negative 1, I'm going to go and draw an arrow going down bottom stairs. And then to the right of positive 2, I'm going to draw an arrow going up to the right. And I'm going straight through each root. So, and I'm done. If I do my work correctly, I should end up exactly where I drew my ending arrows. How cool is that? I'm done, everybody, with that. So, ladies and gentlemen, you have now graphed polynomials that were already factored, and now we have graphed a polynomial that wasn't factored. We factored it, then we found the roots from those factors and plotted them and drew our graph. I want you to watch this video as many times as you need to and practice the homework, everyone. I hope they understood what's going on here. If not, I'll be back in class on Wednesday and I will see you right then. Bye, everybody.